Welcome back. So we're going to do a quick little intro into how reaction rates relate to nuclear reactions. All right, now we've been looking at zero first and second order reactions. Today we're going to be focusing on the first order. When you have first order reactions, they're interesting because their amount of time that it takes for something to decay is set. So that amount of time is called half-life. And it's the time that it takes the original amount to decay by 1/2. So if you were going to write this as an exponential function, the exponent would be 1/2. All right. What materials do we know that decay exponentially at half-lives? So this should be a throwback to radioactivity and nuclear chemistry. All right, where we know that radioactive decay is the spontaneous decay of unstable nuclei that result in the emission of energy, usually in the form of some radiation particle, and smaller nuclei. Okay, so why do we have radionuclei? Why do things decay? It comes from nuclear instability, and that can really result from three major causes. So you can either have a nucleus that's too large, has too much mass, in which case the nucleus would usually emit an alpha particle. Just a throwback to Regents chemistry here, the alpha particle is a 2-neutron, 2-proton packet. It's basically a helium nucleus. So when you emit this particle, it reduces the overall size of your nucleus. You can also have too many neutrons, and this is usually the case. As you tend to get into heavier nuclei, you tend to get neutron heavy, and basically this can cause it just causes nuclear instability. So for these types of nuclei, usually you see beta emission, where a beta particle, as you can see here, is basically a negative charge emitted from the nucleus, and in effect it turns a neutron into a proton. Basically a neutral particle releases a positive charge and becomes a positive particle. Releases a negative charge and becomes a positive particle. Okay. The last type of instability, which isn't as common but does happen occasionally, is that you can have too few neutrons, so you can be proton heavy, in which case you would undergo positron emission. A positron is the loss of a positive charge from the nucleus, in effect turning a proton into a neutron. Okay. Also, just a reminder that any nucleus with an atomic number over 82 is radioactive. There are also some other radioactive elements throughout the periodic table. I believe technetium is one of them, and there's a couple others spread throughout. Also, something to note is that almost all elements do have radioisotopes. So even though generally speaking, for example, most carbon isn't radioactive, there are radioactive carbon isotopes. So carbon-14 is radioactive, and we use it for carbon dating and things like this. All right. Again, you don't have this table for AP chemistry, but as a reminder, this is the different radioisotopes that you can have. This is a small list. This is by no means all of them. You have different half-lives here. So these are half-lives, the amount of time it takes for half of this amount of material to decay. You have the decay mode here with the Greek symbol, and then the nuclide name. All right. And as you can see, generally speaking, the super heavy isotopes, so the things towards the bottom of the screen like uranium-233, uranium-238, all of those are going to undergo that alpha emission because, again, those are super, super massive nuclei, that just need to lose size. If you look up here, for example, like 14 carbon-14, that's a nucleus with 8 neutrons and 6 protons. That's neutron heavy. So as we said before, that's going to undergo that beta decay. And calcium-37 is a good example of a neutron poor nucleus. Calcium has 20 protons. That would leave that nucleus with 17 neutrons, which makes it neutron light, which is very unstable. So again, it's going to undergo that positron emission. And as you can see here, there's a great variety in half-life time. It's very hard to predict the time of a half-life. It's unique to each element. So as you can see here, you have things from as short as 182 milliseconds to things as long as 10 to the 10th years. Okay, so for example, thorium, the planet hasn't even existed for as long as that half-life is. Just to kind of give you an idea of the range of these things. Okay, quick little history excerpt. So Marie Curie is the mother of radioactivity. She is the woman who coined the term. She was born in 1867 in Poland. She lived in France and did all of her chemical work there with her husband, Pierre. She discovered two elements, polonium and radium, and of course, radioactivity. She was the first person to win 2 Nobel Prizes. She was the first woman to win a Nobel Prize. She won the first prize with her husband and Henry Becquerel in physics, and in 1911 she won her own Nobel Prize in chemistry. She also saved millions of lives during the war with her work in radioactive isotopes in medicine. I'm also going to post a video of radioactivity later on that you can kind of just watch for fun. But Marie Curie did a lot of work with radioactivity, didn't know the health effects of the time, and actually when she died, she was very radioactive. Okay, but I digress. So when we're looking at half-life, because it is an exponential function, we can write an exponential equation for this. So basically, you can have the isotope remaining, so A equal to 1/2 times N times the starting amount. All right, so times A naught. All right, so basically, you can have this equation here, where N is the number of half-lives present. All right, so we will look at this. All right, so just kind of showing you, I know that you know what an exponential function looks like, but where large T equals the half-life time. So as you can see here, at each half-life, you have half of the original amount remaining. So after 1 half-life, you have half. After 2, you have 1/4 of the original amount. After 3 half-lives, you have half of 1/4, which is 1/8, etc., etc. Okay, so just kind of another way to look at this, again, looking at kind of experimental data here. At each half-life time interval, which here on this plot you can see the half-life is 24 minutes, you are left with half of the original concentration. So you started with 0.06 molar of N2O5. After 24 minutes, you had 0.03, which is 1/2. After another 24 minutes, you had 0.015. After another 24 minutes, you had half of that, 0.0075. Okay, fabulous. Alrighty. Now we know that the first order integrated rate law is the ln function here, right? So when you plug in for half-life, when you go and solve for, T1/2, basically, and you plug in that 0.5 here, basically what ends up happening is you get A naught divided by 1/2 of A1 naught. So in doing so, you cancel out that term and end up with ln of 2 equals k to the T1/2. All right. Rearranging that function, if you divide by k on both sides, you're left with T1/2 equals ln 2 over k. ln 2 is a constant, that's a number actually. When you calculate that out, it ends up being 0.693 over k. So for any first order reaction, you actually have a simplified equation to determine half-life, and that is T1/2 equals 0.693 over k. And this applies to any first order reaction, not just nuclear stuff, but always nuclear reactions. Okay, so let's look at this example problem here. All right, cyclopropane is the smallest cyclic hydrocarbon. Because its 60-degree bond angles allow poor orbital overlap, its bonds are weak. As a result, it is thermally unstable and rearranges to propene at 1,000 degrees Celsius via the first order reaction. Okay, the rate constant is 9.2 per second. A, what is the half-life of the reaction? B, how long does it take for cyclopropane to reach 1/4 of its initial value? Alrighty, so this is a first order reaction, so I know that I'm going to go ahead and take both of those equations from this page. So I'm going to take that ln function, ln A not over A T equals KT. I like to just have my equations. I'm also going to take T1/2 equals 0.693 over K. All right. Now, they also told us here that K equals 9.2. Okay, so this is what I have. Now, for A, they're simply asking what's the half order of this reaction. Easy peasy, I'm solving for T1/2, plug K into the equation and solve. So when I do that, I end up with, oh bless, my bad. All right, well, we'll look at it. 0.075 seconds. All right, beautiful. Okay, now for part B. How long does it take for cyclopropane to reach 1/4 of its initial value? All right. Basically, they want to know how many half-lives have passed for it to reach, 1/4 of its initial value. So the way that I like to think about this is taking halves of halves, all right? And you can kind of write a sequence for taking halves of halves. Now, if you want to know how many half-lives have passed to reach 1/4, you can just take half of 1 as many times as it takes. So for example, all right, you're going to have 1, half of that is 1/2, half of that is 1/4. Okay, now my end goal was 1/4, so I'm going to stop here. That's what I wanted, 1/4. All right, now, how many half-lives have happened? That would be the number of arrows that you have drawn, right? So 2 half-lives have passed, right? So the question was, how long does it take? So that would be 2 half-lives. You determined the length of a half-life is 0.075 seconds. So 2 times that value would be your amount of time. So that would be 0.15 seconds here. All right, so a little bit of algebra, a little bit of plug and chug. Again, these are pretty simple equations, nothing that you need to memorize. These will be given to you. All right. You don't generally have to worry about the half-life for 0-order and 2nd-order reactions because they change through time. They're not constant. 1st-order reactions are the only ones with constant half-lives. For 2nd-order reactions, the half-life actually increases as the reaction proceeds. And for 0-order reactions, the half-life actually takes longer. So slows down, I guess, as the reaction proceeds. All right, and this is just kind of a summary slide for rate laws. All right, so just kind of some general information that you should definitely be familiar with for this unit. So the original rate laws for 0, 1st, and 2nd order, again, these are determined experimentally from experimental data. The units for the rate constants, as you know, they vary, so paying attention to that. The integrated rate laws, these are given on your reference tables here, but these are things that you need to be able to recognize by sight. So again, you need to know that the 0 order is the original amounts, right? Just the original concentrations here. 1st order are the ln functions. 2nd order are the reciprocal functions, 1 over. All right. And then when you look for those straight line plots, again, you should know the sign of the slopes. 0 and 1st order both have a negative slope, whereas 2nd order has a positive slope. Okay. And for half-life, the half-life equation that you should really remember or be familiar with is the 1st order. That's the one that has constant. It is not dependent on concentration, as you can see. And that's where T1/2 equals ln 2 over K. All right, so you will have some practice problems with this. And good luck.